Hello, in this lesson, we're going to talk about the composition of arc, cotangent, and cotangent. We've done similar things for, for sine, arc sine, cosine, arc cosine, and tangent and arc tangent. And now we're going to do composition of cotangent and arc cotangent. Now, definition. So all of these compositions are compositions of functions. And of course, we want to emphasize the definition of one function one more time, right? Always, all of these have to satisfy the definition of a function if we want to treat them as function. So a function is a rule. So in this section, we're going to deal with two rules. One is cotangent, and the other one is arc cotangent, and the composition of the two in various order. Now, the stage set is still the three pillars of trigonometry. Standard position is where we measure the angles from. Angles are measured counterclockwise, that's a positive angle. Clockwise, that's negative angle. Reference angle is a positive acute angle between terminal and x-axis. And the definition goes by, so here's the setting, right? So A is an angle in standard position, and the point x comma y is on the terminal side of A other than the origin. So we have the R. So we talk about the definition, time and time again. So for cotangent, it's angle is the input and produces a ratio. And we talk about the domain range, right? The domain for arc, for cotangent. So we're gonna do a comparison table as, we tend to do, okay? So cotangent x, or we can use angle if we want, right? It's a rule, right? And that rule takes angle to make ratio, right? Angle is the input and ratio is the output. And the ratio is very specific. It's a ratio between x and y, x over y. Arc cotangent takes ratio and produces angle, right? We talk about all the reasonings, right, in the previous lessons. Okay, so here we're going to be focusing on what we're going to do, which is the composition. But before we do the composition, we're going to review and recap on these, right? So they produces angle. But these angles has to be exactly one for each ratio. So domain for cotangent is any real number, okay? Any real number other than multiples of pi, okay? And k is integer. Arc cotangent, however, the domain, okay, hold on. Let's write down the range first for cotangent, okay? The range is all real numbers. It's all real numbers. And the domain for arc cotangent is all real numbers. But the range, however, okay, the range is an interval from 0 to pi. Okay, so here I made a picture. So I'm going to use the picture that we did with decimal. It gave us a pretty good picture. Okay, so I'm going to use this picture. ArcCoTangent, however, last time I talked about ArcCoTangent, this software doesn't produce a picture. The software cannot produce a picture, okay? So I got a picture for ArcCoTangent, which is right here. So I'm going to just import it over here in the table, okay? So we have a good reference, right? So these are the two pictures. Let's do it this way. You guys can, I think that it should be clear. I think it's clear enough for you. If you have any questions, let me know, okay? It's not as clear as I wished, though. Okay, so our domain range, all of these things set up, right? And we know that these two functions are not inverse to each other. ArcCoTangent does have an inverse itself, right? We talk about that. So what is the inverse for ArcCoTangent, right? What is the inverse for ArcCoTangent? ArcCoTangent, it has an inverse. Its inverse, so let me bring that over, right? ArcCoTangent has an inverse. That inverse is a cotangent, but that domain, instead of these, not the same, right? Not this one. It's not the same domain, but the same range. Okay, so ArcCoTangent inverse is from 0 to pi. 0 to pi. So these two functions are inverse to each other. These two functions are inverse to each other. You can see one's domain is the other's range. Okay, one's domain is the other's range. So basically, it is a piece of the cotangent as we speak of this piece. I think I have that picture done by itself right here. I found it. Right, so I'm going to take this picture as our reference. Okay, as our reference, and I'm going to put it right here. Oh, let me do it over here. Okay. Now, as two functions that are inverse to each other, right? As two functions that are inverse to each other. So these two functions that are inverse to each other, wait. Okay, so this is fine, right? The function relationship, right, is still the same, right? The function relationship is still as the original one. It's just, it has a much smaller domain, And because these two functions are inverse to each other, for the same argument, we speak about any pair, right? Any pair of functions that are inverse to each other, right? So any pair of functions that are inverse to each other. So suppose we call this F, right? And we call this is F inverse. They are inverse to each other. They are inverse to each other. So these two functions that are inverse to each other, right? Hold on. We don't see that little negative sign there. There, for some reason, this is, okay. For these two functions that are inverse to each other, we're going to, for any one-to-one function, right? One-to-one function F, and its inverse, right? F inverse. One's domain is the other's range, right? This is always true. We know the following is always true, right? The composition of them, so F composite, F inverse of X is going to equals to x for x in the domain of F inverse. Okay, great. So these two identities is going to be true. So let me make this just a little bit smaller so we can see more in the same frame. Okay, and the other one is true as well, right? The composition in the other order. F inverse of F is going to equals to X, where X belongs to the domain of F. All right. Okay, so this has been true. We have been using this forever, right? This is the property that's always true. So in our particular situation, F is ArcCoTangent, F inverse is a cotangent in that specific domain, which is otherwise specified. So now we just have to plug in, right? So as a consequence, we will have from here, right? We're gonna copy and paste, and we're gonna compose ours, right? F is ArcCoTangent, ArcCoTangent, right? Composite, its inverse, of course, is a cotangent X. And where X in the domain of F inverse, right? X in the domain of F inverse. What's the domain of F inverse? 0 to pi. Okay, and the next property as a consequence, right? We're going to still copy and paste, right? And we just have to substitute the function into the application. F inverse is a cotangent, right? Of F is ArcCoTangent of X. And X is in the domain of F. X in the domain of F, right? The domain of F is all real numbers. So this second the second one actually is unconditional. It's unconditional, right? Any real number, this is true. So with or without this condition, it's optional. It's optional, right? It's just true for any real number. However, this condition must be attached. This condition must be attached because any cotangent we refer to, we always refer to this cotangent, okay? And when we apply this specific property, it's referred to this other cotangent, which is smaller domain. So we have to specify, So therefore we have two identities similar to the situation of, for sine, arc sine, cosine, arc cosine, we have these identities. So let's see how we use it, okay? The application, using them is fairly straightforward, and you can treat this as a shortcut because whenever we deal with cotangent, we always refer to this one, unless otherwise specified. So if we refer to this one, we will specify it by indicating the domain of that function. I hope that makes sense. Okay, so whenever we refer to cotangent, we always refer to this one. If we refer to this one, we will specify it is that one by specifying the domain. So in other words, if we don't specify the domain for that cotangent, we always refer to this one. All right, so without further ado, let's look at some examples. Let's look at some examples. Okay, example number 1. Okay, suppose we have a cotangent and ArcCoTangent of 5. Well, what would that be? Well, look, this identity applies. This identity applies. Because for this identity, X can be any real number, right? If this is any real number, the result of composition is always going to be X. And so here's 5. It's very straightforward, right? Example number, say, number 2. Suppose I have cotangent of arc, cotangent of, say, -10. What would that be? Well, the answer is -10, right? Still the same, very same thing. Okay, very same reason. In the case, in the event that we forget, right? We're not sure, but then you can do it from inside out. Then you can do it from inside out, okay? Just make sure we understand that arc cotangent is going to give us an angle between 0 to pi. It's going to give us a value from 0 to pi. For example, let me take first one, right? Just in the case that we forget, right? What will happen? So I'm going to take this one, right, as an example, right? We go back to the definition and we don't know, this is not a special terminal for sure. So the other way. Okay, suppose I do it another way. So it's telling me cotangent of arc cotangent is 5. I'm sorry. We know cotangent, suppose I don't know the answer, right? I only know, I want to find out what this value should be. And suppose I forget this identity, or I'm not sure. I'm kind of in a state, I'm not certain. So cotangent of arc cotangent, in this case, and I will first be dealing from the inside. Okay, the inside, I know arc cotangent is going to be an angle. Provide that this angle, okay, is arc cotangent. And because I know the range of arc cotangent, I know this angle is going to be between 0 to pi. Okay, and so I will measure that, and then I also know that cotangent of theta is equals to 5. With that knowledge, not only I know theta is between 0 to pi, which is measured from standard position counterclockwise, right? Between 0 to pi, it means that my terminal is going to be between 0 to pi exclusive, not including 0 and pi. The terminal could be anywhere between these, between 0 and pi, right? So I also know cotangent theta equals to 5. But because this ratio is 5, I know it cannot be in the first quadrant. It cannot be in the second quadrant. Terminal must be in the first quadrant because it's positive. Okay, provided it is here. Okay, provided if it is here, then that's my theta. That's my theta. Okay, if that makes sense to you. In particular, actually, no, this is going to be between 0 to pi over 2, right? The first quadrant. And then my question is almost answered because here I got cotangent of arc cotangent 5, and then I know cotangent arc cotangent 5 is theta. So this is theta. And cotangent theta, it told me this is 5. So by definition of arc cotangent, I can also get the right answer. Okay. In the second case, in example number 2, okay. In example number 2, suppose I'm still going to take this picture, except this time. Okay, if I do the another way, If I do another way, suppose I forgot for whatever reason, right? Then I would just do it from inside out. If I do it from inside out, right? So this time the terminal actually is going to be in the second quadrant. Why? Because the ratio is negative. So in this case, and I know I will still make the same assumption. I say, okay, because I know the output of arc cotangent is going to give me an angle. You can call it theta, you can call it any name you want. And I also know that this angle is going to be between 0 to pi. In particular, because this ratio is negative, right? And I know that cotangent theta is equals to negative 10. So the same argument, right? I measure from the standard position. I know it cannot terminate in the first quadrant, because if it terminates in the first quadrant, it would have been a positive ratio, right? It must be terminating in the second quadrant. Okay, so let me draw a picture. Okay, let me draw a picture so you can see better of this situation. Basically, I'm going to move that terminal to the other interval. Okay, so just give me a second. Okay, so don't worry about what I'm doing here, because this is just the software I use to make a case. Okay, so here I'm just getting everything I need. Okay, so that turned to the other side, right? And I just have to make those marking in the place I want. And my R need to be in the place I want. And there you go, right? So this terminal, this time the theta actually is an angle between 0 to pi. So this is a theta. This is my theta. Okay, in this case, this is my theta. Cotangent theta is negative 10. Okay, so just to give you a visual, so you can see how much information we get, right? So I actually know that this angle is between pi over 2, 2 pi. How do I know that? Because it must be in the second quadrant. The terminal must be in the second quadrant. Okay, and the rest is straightforward. Okay, the rest will be just, okay, with all these assumptions, right? Arc cotangent of negative 10, right? And cotangent, arc cotangent negative 10, I already assume that's a theta. And cotangent theta, I found out, is going to be negative 10. So I still get the same answer. But going through a process that we have to apply the domain and range and our knowledge about cotangent and arc cotangent in particular. Okay, I hope that makes sense. Okay, so that's how we gonna, these are the two examples. So in this case, right, we have two examples now. Let's look at example 3. Example 3, okay? So I got a bunch of examples here prepared, right? Let's look at this one. Okay, so I'm gonna bring my shortcut with me. Okay, so where are my shortcuts? Right, and I have all the information I need. What else? Right, what else information do you think we need? We need to know the domain and range and stuff, right? We need to know the domain and range stuff. In particular, we need to know these two pieces of information. Okay, and that piece too, right? If you like. Okay, so let's copy and paste all of them and bring that with us. Okay, bring that with us. So we put it beneath it. So this way it always follows us, right? Okay, so let's look at some other examples. So we need these knowledge. We need these knowledge, right? That's why we did them first, right? So let's look at the third example. And in this case, I have an arc cotangent, okay, of cotangent pi over 3. Pi over 3. First thing you would think of is that does one of the shortcut applies? Yes, this first one applies, right? This one applies. Why applies? Why it applies, right? The same form, right? Arc cotangent, cotangent pi over 3. So x is, if x is between 0 to pi, this identity will be, fitting. And pi over 3 obviously is in the interval of 0 to pi. Therefore, the answer is just pi over 3. So if we apply this, we got the answer very, very easily. Okay, so recall that we happen to have this case. We happen to have this case. Okay, in the event that we do forget, we can still do the other way. Okay, the other way, which we're going to do it from inside out, pretending that we don't know, right? We don't know this shortcut, right? We kind of forget, right? In that case, we can still resolve this issue, okay? And because this is special angle, okay? So I'm gonna bring my unit circle with us, right? So in this case, we can also use our little unit circle to come to our rescue, right? And suppose we forget about the shortcut. So we kind of have the unit circle. If we don't use the unit circle, we can use this guy, right? We can use one of these, right? So all of these, we have lots of tools. Suppose we actually have the unit circle with us. So we're gonna just do it step by step. Arc cotangent, right? Cotangent pi over 3. So we're gonna do ARD, right? So we're gonna measure the angle from standard position to pi over 3, and we take the red number, divide by the blue number. And so that ratio is gonna be √3 over 3, right? So by this time, we know that, we already know where the output should be for arc cotangent. It's going to be between 0 to pi. In particular, it's going to be in the first quadrant from 0 to pi over 2, right? So you keep in mind that arc cotangent's range, because the range tells us what the answer is expected to be in the range wise. Your answer is not going to be outside the range. If your answer is outside the range, it is wrong for sure. Okay, so with that, and one more step, and we know that for arc cotangent, we chop off the third quadrant and the fourth quadrant. So what angle that corresponds to that ratio, positive ratio? So it's going to be in the first quadrant, and that's going to be, whoops, right? So that is going to be pi over 3, right? You can see that all of these we learned is applicable right here, right now. Okay, so now let's look at another example. Example number 4. And this time we have arc cotangent, cotangent, okay, cotangent of negative pi over 6. Negative pi over 6. Okay, Does any one of the shortcut applies? Does any one of the shortcut applies? It doesn't. It doesn't, right? Does it? This one doesn't apply for sure, right? Does this one apply? It doesn't, because the angle is not between 0 to pi. It's a negative angle. This angle has to be positive between 0 to pi, right? So we can see, right? This piece does not apply. What can we do? What can we do? There are two ways we can do this. Okay, one way. Okay, one way is the following. We just do it from inside out. Just do it from inside out. Okay, so let's do it from inside out. If we do it from inside out, what we are getting here is that we will do it, we do the inside. So we measure the angle. You can see we need ARD, right? We need ARD, cotangent negative pi over 6. So we're going to take the, we're going to measure clockwise negative pi over 6. That's a terminal. And there's a point there on the terminal waiting for us. So √3/2 divided by -½. And that's going to give us negative square root of 3. Okay. Now we know the answer is going to be for arc cotangent of -√3 is going to be an angle in the interval, in the range. It's going to be in the range. And that range, of course, is from 0 to pi. In particular, because this is the negative ratio. Okay, this is the negative ratio. So now we can look at the unit circle. Okay, we can look at the unit circle and telling ourselves, and this is arc cotangent, right? When dealing with arc cotangent, we need to chop off quadrant 3 and quadrant 4, right? So which ratio is -√3? And we look for it, it cannot be in the first quadrant, right? It has to be in the second quadrant. First quadrant, everything is positive. So it cannot be in the first quadrant. So second quadrant, -½ divided by √3/2, there it is, right? Do you see that? -½ divided by √3/2, that's going to be, oh, wait a minute, that's going to be -√3/3. That's not going to make it. -√3/2 divided by ½, that's going to be -√3. So the terminal of that ratio is going to be measured from counterclockwise, because the range for arc cotangent, right, from 0 to pi, 0 to pi, it tells us the angle must be measured counterclockwise because they are positive. Okay, so this terminal corresponds to the angle that's inside the range, and that angle, of course, is 5 pi over 6. So 5 pi over 6. You can see all of these information that we talked about earlier on and throughout will come to our rescue. But I do want to show you another way. You probably will like it this way. Okay. Well, whether you like it or not, I think it would be fun to know that. Okay, so this, starting with this, knowing that cotangent is an odd function, isn't it? Cotangent is an odd function, meaning that cotangent of negative pi over 6 is going to be negative of cotangent pi over 6, right? We can go that way. We can go that way, right? It's negative. So if you go by this way, it will give you a ratio. It will still get the -√3, and everything else everything else pretty much the same. So arc cotangent, right? So here, it make it easier to find the ratio, okay? Because if you do cotangent pi over 3, you're gonna get a root 3 over, you're gonna get root 3, and there's a negative root 3. You still get the same thing, but it just, you use the odd number, the odd function property. You still get the same answer. You still get the same answer. But wouldn't that be fun to use it? Yes. Okay. So let's look at another example. Okay. I have prepared some examples for you. So this should be example number 5. Is it 4 or 5? Let me see. 5. Okay. And this one is our cotangent of cotangent 2 pi over 3. Does any one of the property applies? I think it does, isn't it? This property applies, right? This identity applies because 2 pi over 3 is right inside of 0 to pi. So the answer is just 2 pi over 3, right? So that property applies. That's nice, right? So you can see, if you know the shortcut, you totally know what you're doing. It's nice. What if you don't know? Well, that's not going to be the end of the world, right? So another way is still just do it from inside out. Okay, pretend we don't know, right? So I want to show you how each piece of information is being used, right? Pretend we don't know. We do it from inside out. We do it from inside out. So I'm going to take that unit circle with us, right? And hold on. Okay, another way, right? So pretend we don't know. And in here, what we can do is that 2 pi over 3 is a, hold on, 2 pi over 3 is a positive angle. So we just measure it. So we're going to do ARD, right? From standard position, we measure up to 2 pi over 3. And on that terminal, there's a point waiting for us. So we do it from inside out. So arc cotangent of 2 pi over 3. So we're going to take the negative half divided by root 3 over 2. And that's going to give us a negative root 3 over 3. Okay. And this ratio, of course, is going to land us, right? We know that. And now, once we do that, I'm going to clean that up. Once we've done that, we're dealing with arc cotangent. We're dealing with arc cotangent. When dealing with arc cotangent, chop off root 3 and quadrant 3 and 4. And what do we get? Right, we have a one-to-one correspondence, angle and a ratio. So for that ratio of negative root 3 over 3, the red number divided by the blue number equals to negative root 3 over 3. It cannot be anything in the first quadrant. It has to be on the second quadrant, right? It has to be in the second quadrant. So we found it. It cannot be this one. It cannot be this one. It must be this one. And the range of arc cotangent tell us the angle must be measured counterclockwise. Okay, so this way you still get 2 pi over 3, and there's no way to escape it. To escape that right answer. So you get it for sure. Okay. All right. So without further ado, let's look at another example. So this one is example number 6. Okay, number 6. We have an arc cotangent of cotangent of 4 pi over 3. Okay. In this case, the shortcut doesn't work. Okay, the shortcut doesn't work because 4 pi over 3, this guy does not apply. Okay, does not apply. So then what do we do? Well, we just do it from inside out. We just do it from inside out. Okay, we do it from inside out. When we do it from inside, right? So our cotangent 4 pi over 3. We're going to do ARD another time, right? Always ARD will take us somewhere. We counterclockwise measure 4 pi over 3. I think we terminate here. Pi over 3 is a pi plus pi over 3, right? So that's pi over 3. So there we go. We got a terminal. On that terminal, there's 2 red numbers waiting for us. Red and blue. Red and blue. So the red divided by blue, negative divided by negative is going to be a positive. So we get a √3 over 3. We get √3 over 3. Okay, so next we're going to get to the next stage. Okay, what is the next stage? Well, the next stage is that what's our cotangent of √3 over 3 equals to? So we're dealing with ArcCoTangent case, and we know that quadrants 3 and 4 are gone. ArcCoTangent of √3 over 3 is just going to be which ratio give us √3 over 3 and that terminal. This is going to be 1-to-1 correspondence, right? And the output is going to be between 0 to pi, right? The answer, we know this answer is going to be between 0 to pi. In particular, the ratio is not negative. The ratio is positive. So we know the terminal is going to be in the first quadrant. So which one of these ratio gave us √3 over 3 here? Okay. Half divided by √3 over 2 is going to be √3 over 3. And so here we go. The answer is going to be pi over 3. That's it. You see, right? All the information we talked about, they are useful right here. Okay, example number 7. Okay, so let's look at another one. ArcCoTangent of CoTangent, in this case, right? In this case, it's a negative. I have a negative 5 pi over 3. For sure, this does not apply. Does not apply, right? It's negative angle. This only applies between angles between 0 to pi. So this doesn't apply either. So what do? The same drill, okay? We do it from inside out. We do it from inside out. Okay, so ArcCoTangent waiting outside. And we're gonna deal with cotangent negative 5 pi over 3. So to measure the angle, right, ARD, from the standard position measuring clockwise, this is 5 pi over 3. So this is a pi, right? 5 pi over 3. So we need another 1 pi over 3, 2 pi over 3, right? So here we go, 5 pi over 3, right here. Okay, and at the terminal, we have half divided by √3 over 2. So the ratio is going to be √3 over 3. Wait a minute, how did that come out? Okay, I'm gonna put it inside, right? So what will be the answer? We just did that, right? We just did that, but you just have to know that when this time we're dealing with ArcCoTangent, √3 over 3. Chop it off, right? Positive ratio terminal is going to be here. And it's going to be, you find that ratio that corresponds to, that angle measured from standard position counterclockwise, because we know the answer has to be between 0 to pi because the range of arc cotangent tell us so. So the answer, wait, go away. So the answer is going to be pi over 3 one more time. Okay, so these are the examples that I think we have covered thoroughly. Okay, and all the examples you're going to see and all the homework questions, and they're going to be one of these kinds, right? You're going to apply definition, domain range extensively. So that's all for this lesson, and I will see you next time. Thank you for watching.